Welcome to the Explainer. Today, we're going to tackle a classic coding interview question. You know, it's one of those problems that looks really tricky at first, but the solution, well, it's actually beautifully simple. We're going to rotate a linked list.
Okay, let's dive right in. So here's the puzzle. You've got this list of items, and you need to take the first few, let's call that number K, and just move them to the end. But here's the catch. Think of it like a train. You need to move the first few cars to the very back, but the train can only go forward. How in the world do you do that?
To crack this thing, we first have to get a really solid grip on the core challenge here. And it all comes down to the nature of a singly linked list. That's what makes this a puzzle in the first place.
So, let's stick with our train analogy. Each car, that's what we call a node. And the little coupling connecting it to the next car, that's the pointer. And here's the most important part. It's a one-way connection. Each car only knows about the car right in front of it, and that's it.
Right, and this is the crucial constraint. Once you move past a node or walk past a train car, there is no easy way to get back. It's a one-way street, and that's exactly what makes moving the front of the list to the back a real head-scratcher.
So how do we solve it? How do you get those front cars to the back on a track that only goes one way? Well, the big idea here is surprisingly elegant, and it's all about, well, it's about temporarily changing the rules of the game. First things first, we're just going to walk the entire list, from the very beginning, the head, all the way to the end, the tail. We need to find that very last node. In our analogy, this is us just walking from the engine all the way down the train to find the caboose.
Okay, now this is the trick. This is the big aha moment. We take that last node, our caboose, and we connect it right back to the very first node, the engine. And just like that, we've turned our straight line into a temporary circle.
Now that our list is basically a circle, believe it or not, the hard part is over. To find our new finish line, we just move forward K spots from the beginning. The spot where we land, that is going to be the new last node of our reorganized list.
And for the final move, it's simple. We just uncouple the train at this new position. The node right after the break, that becomes our new head, our new engine. And by breaking that link, setting its pointer to null, our circle becomes a straight line again, but now it's perfectly rotated.
Okay, so that's the big idea. It's a pretty cool concept, right? Now let's see how this all translates into actual working C code. It's probably simpler than you think.
So this little piece of code right here, this is our step 1. It's just a simple loop that keeps hopping from one node to the next until it hits the end. This is literally the code that walks the train to find that final caboose.
And bam, this single line of code is the magic trick. It takes the next pointer of that very last node and points it right back at the beginning of the list, the head. This is the instruction that creates our temporary circle. It's so simple. And what's this loop doing? Well, it's just walking along our new circular track. It's methodically counting off the K spots to find the exact place where we need to make our cut, which is what's going to define the new end of our list. And this is the finale, a really slick two-part move. The first part reassigns the head of the list to be the node that's right after our cut point. The second part breaks the circle by setting the previous node's pointer to null. And just like that, the rotation is done. So we have a solution, and it works. But in computer science, that's never the only question. We also have to ask, is it a good solution? And to answer that, we need to talk about efficiency. We usually measure how good an algorithm is in two key ways. First up is time complexity, which is basically how much longer does it take to run as the list gets bigger. And then there's space complexity. How much extra memory does it need to get the job done? So for time, our algorithm has what's called O of n complexity. It sounds a bit technical, but all it really means is that we only have to pass through the list once. That makes it really, really fast, and it scales perfectly no matter how long the list gets.
And the space complexity, it's O of 1, which is frankly amazing. This means our solution uses a constant, tiny amount of extra memory, just a couple of variables, whether the list has 10 nodes or 10 million. It is incredibly resource efficient.
So why does all this matter, beyond just passing a coding interview? Because the lesson here is so much bigger than just this one problem. It's about a powerful pattern for creative thinking.
And here it is. The real takeaway is that by changing our perspective, by temporarily transforming the very structure we were working with, we found a dead simple and super efficient solution to a problem that seemed really complex. We made an impossible operation possible.
And that leaves us with a final thought from this explainer.
A question for you to chew on. What other unbreakable rules in a problem you're facing, whether it's in code or just in life, could you maybe bend, just for a moment, to find a brilliant breakthrough?